Okay, so power functions. Power functions are kind of the building blocks of a polynomial function. It's just of the form f at x equals x to some power. So we talk about that x, the variable being in the base of the exponential expression. And the exponent, of course, is a number. It's not a variable for it to be a power function. So this is different than what's called an exponential function. Okay, and the exponential function is where you have the exponent in the, or you have the variable in the exponent, and you have the base as a constant number. And so that's Math 14 territory. We're not going to touch that at all in this class. So if you want to just make a mental note that that these are power functions and exponential functions. Really, the difference isn't so much in the words; it's just the convention that we use to describe them. So power functions is x to a power. An exponential function is a number to the power of x. Okay, so just keep the language straight there.
So in that case, that a actually would be like number 12.
Yeah, it could be like 2 to the x is an exponential function. X squared is a power function. Okay? Okay, so in these toolkit functions that were introduced back in Chapter 1 of the pre-calculus book, we have two power functions. One is just x squared, and then the other one is x cubed. And so x cubed is that blue line, if you can see the difference between there. There's a difference in behavior between the x cubed and the x squared. And so what I did was I went through and I made a whole bunch of graphs and laid them all on top of each other. And you can see what's happening with power functions. Okay, with a power function, there's no coefficient in front of it, at least for the purposes of this discussion. So that f at x squared is the inner green one. That's the one that's the parabola. It's obviously a parabola. Then f at x cubed is the blue line that comes up from a negative number, goes through 0, and then becomes f at x becomes positive, and it increases without bound. And notice they all intersect where x equals 1, right? X to the any power is 1. So you would expect them. But as we're going to increase the power, so here's x to the 4th, you see how this thing is still generally shaped like a parabola, but it starts to flatten out along the axis. In other words, from -1 to 0, it goes down to the axis very quickly, and then it goes to 0, and it stays close to the axis until it shoots up to 1, and then it actually goes inside of x squared beyond 1, and it gets to bigger numbers faster, as you would expect, right? Because 100 squared is less than 100 to the 4th. And so you have this thing. Now with the odd ones, like this x to the 5th, it looks a whole lot like the x cubed, except that it's a little bit wider, still goes through 0, and then it goes up on the other side. And then we have x to the 6th, which is that kind of tan one. It's just, well, I didn't put a dot there, or maybe I did, but yeah, I did. And then x to the 7th, and I'm going to stop at x to the 8th because they start getting really, really close. But you notice the kind of qualitative difference. This thing sort of flattens out close to 0. But all of the odd ones retain the sign. So if you're evaluating -1 or -2, x equals -1 or -2, the function is negative. With a even exponent, you always get a positive number. So there's a kind of a big difference between the odd exponents and the even exponents. On the positive side, they all kind of behave the same, right? A positive number gives you a positive number. But with a negative x, you'll get a positive f at x when the power function has an even exponent, and you get a negative number when it has an odd exponent.
So the x cubed one also gets flatter as it gets bigger?
Well, it goes through 0. The flatness I'm talking about is when it's close to 0.
Okay.
Okay, so here I'll just kind of summarize that with even exponents. As x is greater than 0, as it increases, the function increases, and when it's less than 0, as the function decreases, meaning you get from -1 to -2 to -3, that's decreasing. F at x increases. With odd exponents, we're looking at the same kind of behavior on the positive side, where as x increases, f at x increases, but on the negative side, as x decreases, we're going to find that f at x decreases as well. So -2 cubed is going to be -8. So the general shape is like this. So it looks an awful lot like the x squared and x cubed. It's just that area that's right around 0 will flatten out more. So if we want to take a quick look back at that just for a moment, I'll come right back to this slide, but let's look at this one again. You see what I mean by that flatness. Look at that f at x squared, kind of comes down gently towards 0, and then it increases beyond that, but as you get to higher and higher powers, you get that flat spot in the middle. Okay, any questions so far? Now, power functions in themselves, there's not much going on with them. To really get some interesting functions, what we do is we add these, we multiply those power functions by a constant, a coefficient, and then we add a bunch of them together, and so we'll get a polynomial. The word polynomial, the nomial part means the root of that is the same word as the word name, and so poly means you have many, essentially potentially many different power functions that are added in this fashion. Now, I've written this backwards probably from the way that you've seen it most of the time. And in fact, we only write it this way in some special circumstances. This is just to illustrate that we, instead of having different letters for the coefficients, we can call the coefficients by A0, A1, A2, A3, and it's most convenient when you make the subscript the same as the power. So more commonly, we would put it in this order, and each one of those power functions that has some coefficient in front of it is called a term. Now, the highest degree that you have in the polynomial is tells you a couple things. We call that the leading term, and it's the polynomial degree. So a polynomial of degree 4 has one term that has an exponent of 4, and it is the highest exponent in the polynomial. So we call a power function of a 4th degree power. This polynomial would be a 4th degree polynomial. It may or may not have x cubed, x squared, x, and a constant term. Here you can see I don't have any x squared. That's fine. It doesn't change it. We still talk about the leading term as being the having the degree of the polynomial. So, and we also refer to that 3 as being the leading coefficient. So when I'm talking about a polynomial in general and I say the leading coefficient, what should occur to you is that look for the term with the highest degree, and it's the coefficient that's in front of that. So the thing about coefficients is that we include the negative sign with the coefficients. That just makes it more convenient to deal with. So that second term, the coefficient there is a -1. Right? That 1 is implied, and we say negative x cubed. That actually has a coefficient of -1. Oops, I know I went a little too fast there. Okay, anybody have any questions on that? Hopefully you've seen at least some of this before. Okay, so now let's think about polynomial behavior. what we call the long-run behavior, that means when x gets very, very large, big numbers, or very, very small, like -1,000, -1,000,000, you know, very small numbers like that. So if we look at a polynomial, we look at the leading term, and in this polynomial, the 3x cubed is the leading term. Now, the long-term behavior of this is going to be similar to the power function f at x equals x cubed. So what this means is, now here's that notation that I introduced a little earlier with the arrow, that we say, as x goes to infinity, f at x goes to infinity, and as x goes to -infinity, f at x goes to -infinity. So what this means is that if I'm making a graph, that once I zoom out on this thing and look at the long-term behavior, I'm going to expect the graph to go to the upper right, and I expect it to go down to the lower left. So following generally the pattern of x cubed. Now it may do other things in the middle, and we'll consider that separately, but ultimately that leading term is going to dominate the behavior of this polynomial. To the point where maybe the other terms aren't even that consequential. I mean, think about if you were to evaluate this thing at x to the 1,000. Okay, so then you'd have 1,000 cubed, which would be what, 1 billion? So that first term would be 3 billion. Then you'd have 1,000 squared, which is just 1 million. And 1 billion, of course, is 1,000 times more than 1 billion. So even at a number like 1,000, that first term really dominates. Everything else is more or less lost in the rounding, so to speak. So that's what we refer to with long-term behavior. It's going to look like it behaves like 3x cubed. So the short-run behavior now, you don't really hear the words short-run behavior that much. We really talk about perhaps the local behavior or the behavior around 0 or the behavior around the roots or something like that, but anything in the middle. Kind of the key thing that tells you what's going on are the intercepts. So the y-intercept, of course, is the easy one to get to. You just stick in a 0, and lo and behold, you just get the constant at the end. So f at 0 of this thing is just 0, 6. So if we look at the y-axis where x equals 0, it's going to go through the y-axis when at y equals 6. Now with the x-intercepts, what we do is we say, okay, the function has to be 0 to go through the axis where y equals 0. And so with something like this, there's a number of ways to find the zeros. The way that's perhaps the most convenient is to factor it. And I know all of you have factored that in your mind even before that came out, right? Yeah, right. Most of what you've learned about factoring, you factored mostly quadratic equations, x squared involved equations, and occasionally the x cubed. I'm not going to torture you with making factors of polynomials of degrees 5, 6, and 7 because, in fact, nobody really does that by hand. You do it generally with some type of a computation device. So for the purposes of this course, the factoring that you'll be doing is the factoring that you're familiar with, or more likely we're going to start with a factored form, or I'm going to give you the factorization. And so once you see it factored, this tells you where all your intercepts are on the x-axis, right? So your intercepts are going to be 1/3 and 0 for that first factor. The second factor is 3, and the 3, 0, or the root, I should say. And the third one is -2 and 0. So if I plug in a 3 to that polynomial, that 3x cubed and so on, that thing's going to evaluate to 0. So that's the nice part about factoring, is that using the zero product principle, one of the factors has to be 0, and those are the 3 cases where it would be 0, where x is 1/3, 3, or -2. So you should be able to identify those when you're looking at a factored form. Okay, so let's think about what we know from what we know so far, and I'll add in a couple things. If we see a graph of something, now we don't know exactly what that graph is about. I didn't put any scales on there, and you can see that it goes through the x and y intercept's pretty close to the origin, and that's about all you know. It has three roots, 3 places where it goes through the x-axis, and any function will only go through the y-axis once, right? Because if x equals 0, you're only supposed to get one value out of the function, so you're only ever going to have one y-intercept with a function. So what do we know about this? We look at the long-term behavior, and we know it's an odd power, right? Because the odd power, as you go negative, becomes increasingly negative, and as you go positive, is increasingly positive. Now we can flip these around. If we had the leading coefficient as something negative, you would expect that it starts in the upper left and ends up at the lower right. So really the point here is that the long-term behavior goes to opposite signs. So in this case, you would expect a positive leading coefficient. If it was just the opposite of that, where it came up from the left and went down to the right, you would expect a negative coefficient. But the point is that it would be an odd power. Now, the maximum number of roots that a polynomial can have is the degree of the polynomial. So in other words, if you have an x squared function, you can at most have 2 roots to that. An x cubed function, you can at most have 3 roots. An x to the 5th function, a 5th degree polynomial, you can at most have 5. You don't have to have 5, but you have at most 5. Okay, so if we know that, then when we look at this graph, we say, oh, it has 3 roots. So that must mean that the degree of the polynomial has to be at least 3. Now, it could be 5, it could be 7, it could be any odd number, but we know it's an odd number and it has to be 3 or more. Now, the other thing is that, and I think this is a new term, I haven't talked about this before, is these turning points. And look at the local minimums and maximums as turning points. The most turning points you can have is 1 less than the degree. So think about a parabola, for instance. A parabola has 1 turning point, right? It gets to either a minimum or a maximum, and then it goes the other direction. So that's a secondary polynomial. 2 minus 1 is 1. Now this thing, we're saying, has to be at least a 3rd degree polynomial. So if I take 3 minus 1, that means that I have at most 2 turnarounds. So that's consistent with my other 2 conclusions, that maybe it doesn't really go through the axis and I can't count up the roots that way. I certainly can count the local mins and maxes as turnaround points. So the conclusion that we draw from this graph is that we can say it's at least a 3rd degree polynomial function. And probably the other element that we can put in there is that the leading coefficient is positive. Okay, any questions?